Okay, so it's 20 minutes now, and I think it's time for our third keynote speech. Then, so Tristan, can I just turn it over to you?
Yeah, okay. I will
Okay,
share
thank you.
my screen. Thank you. Uh, so, uh, it's my pleasure to introduce I-Chen Wu. So, I-Chen has a PhD from Carnegie Mellon University that he earned in 1993. And he is professor at the Department of Computer Science in NCTU, so National Xiaotong University. And he is also co-editor-in-chief of the ICGA journal, together with Mark Vinant and I. So I-Chen has multiple achievements that he made. So first time I met I-Chen was in 25 in Taiwan at the Advance in Computer Games conference, where he explained the game of Connexis that he had invented. So since then, Connexis has been played at many computer Olympiads, and it's quite a popular game. And it is also played by humans, so as an enjoyable game on game website. So the second time I met I-Chen was in NCTU, and he invited me in 2016 after the AlphaGo win against Lee Sedol. So I had a talk there, and I meet his students. So he has a large group of students who are working on game playing and who are making very strong game playing program. And at that time, in 2016, just after AlphaGo, he already had a very strong Go program that was trained with deep reinforcement learning. So this was my introduction to I-Chen, and now I will stop sharing my screen and will give the screen to I-Chen for his talk. So I-Chen, the floor is yours.
Okay, thank you, Tristan, and the chair of Zhuxian. I happen to clear my screen. Okay, let me start it again. Okay, can you read that? Okay, read my slides.
We don't see your slides.
Okay, let me try again.
Now it's okay.
Okay, good. Okay. Okay, so okay. Okay, hi everyone. Okay, Tristan and Zhuxian and Michael. Well, thanks for hosting this. Okay, it's my great pleasure to present my talk about a research journey on deep reinforcement learning in the past from computer games and beyond. I'm I-Chen Wu, from National Yangming Jiaotong University. Okay. Okay, this is the outline of my talk. Okay, from computer games and AI and deep reinforcement learning, and then show what I have done in about my research on deep reinforcement learning applications. Okay, include computer games and so on. Okay. Okay, so go back to computer games and AI. Okay, and I would like to start off by these slides. Okay, just as the full fly of artificial intelligence. Actually, this term, this phrase motivated me to started my research on computer games. Okay, because we know, okay, computer games, chess is a typical computer game topic. Okay, and to study artificial intelligence, you better know how to solve playing chess first. Okay. Okay, so and this also shows probably the key of the whole the whole of my talk, okay? Because I would like to tell you, okay, what I have done for computer games, then go to all kinds of application, not limited to computer games. Okay, and we all know there are two milestones in AI and games. Okay, first of all, it is Deep Blue beat Kasparov, a chess champion. Okay, who ranked #1 at the time, the youngest ever world champions for probably 12 years. Okay, and so that would be a very, very big news. And many of our people in the ICGA society was involved in that event. Okay, so like Yap and Jonathan. Okay, and this is the picture shown. Okay, at that time. Okay, particularly for Game 6, the key that Deep Blue won the match. Okay. You can see the scenario. It's quite similar, right? Okay, like okay, of course, I will talk about AlphaGo later. Okay, and this is the book, the cover page of the book. Okay, Artificial Intelligence: A Modern Approach. Many teachers call this book is a kind of Bible for artificial intelligence. And in its cover page, okay, it shows the winning game, 6, okay, the winning games, okay. So it shows the importance of this event, okay. That will make, okay, many, it's a very, very critical event, okay, for artificial intelligence, okay. And then, okay, Johnson and Yap, okay, say, okay, said this in 2002. He said, okay, Go has emerged as a major challenge to AI research because, okay, we can have a chess program that beat the grand champion, but still not for the game of Go. Okay, so Go becomes, okay, or emerge as a major challenge for to AI research. Okay, and indeed, okay, it has been a very big challenge to AI society. Okay, ICGA society. Okay. When as most of us know, okay, a very big event is demise AlphaGo beat Licedo in 2016. Okay, and Licedo had won the most world champions titles in the previous 10 years. Okay, previous means at that time before 2016. Okay. He won many world champions. So okay, it's 4-1. Okay, I think many of you still remember this event. Okay, and the left one is Agile representing on behalf of AlphaGo to play with Licedo. Okay. And actually, I would also like to let you know, okay, Ajia Huang is also a key member in our society. He participates in ICGA events almost every year. Okay, all right, yeah, okay. So I would say he grew up with, okay, ICGA. Okay, I think we all are proud of him. Okay. Okay, the impact of the event of the AlphaGo, okay, is quite huge. Okay, in at least the following two sense. When compared with Deep Blue, okay, it has a big gap to beat human Go champions. Okay, okay, most people thought this would be a decade away. Okay, and the other is, okay, not much Go domain knowledge is used. one of the key is deep reinforcement learning. Okay. Actually, this is also related to my talk. Okay, this time. Okay, because since we capture the key of the deep reinforcement learning, since it does not need a lot of domain knowledge, that also implies, okay, we can apply deep reinforcement learning to many other kind of application, okay, easily, okay. 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 Oops. Okay, so now let's quickly review, okay, reinforcement learning, okay, or deep reinforcement. I think many of you already familiar with this, okay. Reinforcement is kind of AI computational approach to learning from interaction. Okay. The agent, okay, read, okay, the state of environment, and then decide to take an action. And then the environment will react this action with a new state together with a reward. Then the agent read the next state, okay, repeat to take an action. And then the whole thing keep repeating the interaction process again. Keep repeating, okay, to find the most, okay, cumulative, okay, to maximize the cumulative reward. And I just show some example, okay. Like this is the game of 2048, okay. Wow, it's quite popular 10 years ago. Yeah, right, 10 years ago, 2014, okay, yeah. And okay, the game is very simple. The agent only need to decide up, down, left, or right, okay. And in this case, it decide to say, okay, move to the right, okay. So all numbers shift to the right, okay, and merge with the same numbers, which becomes its reward. So the environment return the reward and react this action with a reward and to a number 2 or 4. And then the agents do that again. Okay, say okay, move up. Okay, and then keep doing everything again. Okay, so keep running again. Okay, until nothing. You cannot make any move. Okay, and then we can see what's the score. Okay, the total score. Okay. Okay, so the next example, like the game of Go. Okay, I think many of you are familiar with or are doing like chess, whatever games. Okay, many are two-player games, and like the agent could be a program or a human. Okay, the agent say, okay, it's our CGI Go program. Okay, then the environment will be the opponent, okay, Kejie, okay, who was ranked number 1 at that time, okay. And then when we play, our program play with Kejie, okay, we read the whole board like this, okay, and then decide to take an action, okay, say C2, okay, play here. Try to prevent break stone escape away. Okay, and then of course for coach the environment will react with one stone trying to escape. Okay, this group. Okay, and then we try to block it again. Okay, and then at this point, okay, coach realized he cannot escape away, so he resigned. Okay. So we got 1 point, okay? Okay, so a lot of games can be formulated as reinforcement learning easily, okay, like this. In the past, just now I showed you 2 examples, okay, with games, okay. But what about others? Okay, for example, like racing car, okay. This is a racing car for AWS Deep Racer. Okay, it's a miniature one. Okay, I don't quite remember. It should be 1 to 14 or maybe 10. I don't remember the exact number. Okay, so it's a miniature one. Okay, and in this car, there's a camera in front of it. Okay, and this camera read the whole picture. Okay, and then based on that, it decides to go straight, but it might also want to make right or make left turn. Okay, say it feel need to make a little bit right. Okay, like this, and then you get some points from that because the car is still on the track. Then what if the car decide to turn left? Since it might go out of track, okay, then we give it negative points, okay, to discourage the car, okay, not to go that way, okay. So this is also another reinforcement learning example, and actually from this example, you can see a lot of applications can follow this kind of reinforcement learning model, okay, or paradigm. Deep reinforcement learning is actually combined from deep learning and reinforcement learning, okay. Deep learning, okay, like this one, okay, it reads pictures, okay, all right. So it use some kind of deep learning process to see which way to go, okay. Actually, like the goalball can also be viewed as a kind of deep learning stuff, okay. Okay, so then we can see, okay, deep reinforcement simply combine both key learning methods together. So it can reach end-to-end solution. And one key of the challenge is, okay, is extremely high dimensions. If we go back to see this one, okay, for deep learning, the dimension is already very, very huge, like say 100 by 100 picture, then the dimension would be 10,000. Okay, and for the interaction, okay, you can think the dimension is much higher. Okay, so this is a very big challenge for deep reinforcement learning. Okay, and typical two successful examples in the past decade, like AlphaGo and deep Q-learning for Atari games, both are from DeepMind. And actually, there are many other successful stories. For example, like this. Okay, computer games. Okay, of course, there are a lot of computer games. Okay, including some video games like OpenAI 5, AlphaStar. Okay, and actually, for some other applications like robotics, okay, autonomous driving racing, okay, and some optimization problem like chip design, okay, faster graph placement by Google Brain, okay, and optimizing matrix multiplication like Alpha Tensor and job shot scheduling, okay, and even for with RLHF, okay, for the large language model by OpenAI, okay. So actually, there are many successful story, okay. So in my past 2 or 3 decades research, okay, here I would like to show what our journey, okay, research journey related to deep reinforcement learning. Of course, we started from computer games, okay. For the computer games, we have done a lot for the game of Go. and some other games like the game of 2048, okay, the game of Chinese chess, the game of kinetics, okay. So let me start by, okay, the game of Go, okay. Actually, I would like to say, okay, one of the key contributor is Tilong Wu, who was the chair of the previous session. Okay, yeah, you already saw him. Okay, and in 2017 or 18, okay, we proposed a multi-level value network for computer goals. Okay, he is a key member. Okay, he is a key designer. Okay. Basically, this one, we follow AlphaGo's principle, but in AlphaGo, it has two heads, one for policy and one for value. Okay, and for the value head, okay, it only output the win rate for the whole game. But actually, at that time we realized, okay, not just one. If we can output all many win rates for different common, okay, then that will just like multitasking, it will greatly improve strength. Okay, common is points added to the second player. Okay, to balance the game. Okay. Yeah, so you can see, okay, in our case, the value is not just one, okay, one win or lose. We say, okay, if we the common is 0.5, what is the win rate? 1.5, what's the win rate, and so on. Okay. With this, okay, the net can accurately capture the key information, and the network becomes more powerful. Okay, yeah. So in our research result, okay, we improve our strength a lot. Okay, up to 67%. Okay, and we this way we can also use this way for handicap games. Use dynamic homing. It's a techniques probably 10 years ago. Okay, commonly used 10 years ago. Okay. And based on that, okay, we can also improve a lot. Okay, you can see this result. Okay. Next one, we use population-based training to improve and accelerate AlphaZero training. Okay, also by Tilong Wu. Okay, and Ting Han. The review, the work, okay, is related. Let me quickly review AlphaZero. Okay, AlphaZero is a very elegant method. Okay, it asks the model to make a move to perform Monte Carlo tree search. With like several hundred simulations. Okay, since it has several hundred simulations, the quality is definitely better than just one. Okay, so we use the higher quality move. Okay, and then go back to train the model. Okay, so this is just like a tutor, teacher, and then teach a student how to make it improve the learning. Okay, and then so in this way keep improving. Okay, so you can learn from with zero knowledge, very dumb program, and then go up all the way up to the superhuman. Okay. And then we at that time, but the problem is it takes a lot of computation resource. So we got to solve this problem because we don't have that much computing resource. You know, like we cannot. Definitely our computing resource cannot compete with DeepMind or Meta. Okay, their computing is definitely 100 times, at least 100 times better than us. Okay, so we got to find some smart way to do that. Okay, and we propose population based to train some hyperparameters. Okay, population based training is kind of evolutionary method to tune hyperparameters. Okay. And this result was published in Triple AI 2020. Okay, and we at that time we achieved a state of the art. Okay, a win rate of 74% against the ELF OpenGo, which was the state of the art at that time. Okay. Next, the next research topic is about strength adjustment for MCTS-based progress. It was published, presented in Triple AI 2019, and also in CIM, okay, Computational Intelligence magazine, okay. Okay. In this work, okay, we find out we developed a kind of strength index Z. Okay, so we can use we can adjust the Z easily, change the strength. Okay, for this range, okay, then we can derive, okay, we can cover about 800 euro rating. Okay. And together with many of our previous version programs, okay, like CGI 1.0 to 4.0, okay, then the full program can cover almost through 3,000 euro ratings, and we test that with some players, okay, for professionals in Haiphong Go Association in Taiwan, the biggest association in Taiwan at that time. And we also test that for 10 level amateur, Q level amateurs. For professionals, okay, our result shows quite consistent. Okay, the R square number is 0.66. Okay. And at that time, we already identified a very good player, Xu Haohong, who has just won, okay, the champion in Asia Olympia. Okay. And for 10 level, okay, the consistency is quite good. Okay, and the Q level amateur is also okay, but of course, if we go back to see, okay, 10 level is more close, okay, because our conjecture is, okay, 10 level players would be more stable, okay, and the Q level amateurs strength could be fluctuate very unstably, okay. So this really shows the real case, okay. And then we go to the direction of solving life and death problems, okay. And I think it's quite interesting to see that, okay, solving games is also emerging as a very important thing, okay. Like the previous keynote is about solving Othello, and the next keynote by Yap also talking about solving chess, okay. But anyway, let's see. Okay, we also trying to solving the game of Go. Okay, but we focus on life and death problems. And our first work related to that is this paper. Okay, presented in Triple AI 2022. Okay. by 仲敬师 okay, 仲敬师 and also guided by Tirong Wu. Okay. The key idea of this work is to propose a new approach called relevance zone-based search to solve life and death problem. Relevance zone and the lambda search are the work done by Thompson, okay, in 2000. Okay, if some of you might already remember, okay. This would be a very important key, okay, to solve, okay, the game of Go, okay. In our method, we try to solve search first, but we have a little bit different from their work. In lambda search, they make a normal first and then use relevance zone to solve it. But in our method, we just straightforward use search, okay. And then once you find a winning move, then the winning move's relevance zone will be used to prune other moves. Okay, so it's a little bit different, but based on this, we can incorporate most best first search. But the traditional one, you cannot use that. Okay, because you got to make a no move first. So that would sounds a little bit strange because you know you got to that sounds like you got to make a bad move. Okay, no move you can think bad move is no move is doesn't move anything. So of course it should not be a very good move. Okay, and then go back to find good stuff. Okay, but in our work, okay, we straightforwardly just try the best one. Okay. And then once we find a winning move, then we use the winning moves, okay, our zone to prune others. Okay, so that's a little bit different. Okay, let me illustrate that in this simple example. I hopefully that will help you to understand this method quickly. Okay. For example, if you are a Go player, you know, okay, the white one is alive. Okay. It already have one eye. So you got to kill another eye, okay, for black. So to do this, okay, first, it might try to play it here to prevent white to make a new eye here in this territory. So after that, okay, then white make 2-4 to make a new eye. Okay, so end up with 2 eyes alive to be alive. Okay. But if we want to prove that, okay, actually we need to try all kinds of ways to prevent white from making two eyes. Okay, so okay, black might try this one. Okay. Then okay to not so white won't be able to make the second eye, but in this case, white can make 4-6 to make a bigger eye here. The same thing, okay, we can use 5-7 to prevent that to make a new eyes, okay, but end up with 8, okay, the whole thing we can conclude that okay, white can in any case it can make an eye here. And based on this, okay, we also can get a relevance zone, okay, here, okay, because that indicates, okay, black need to play any of these. Otherwise, white can make an eye here, okay. So okay, this give us a clue to say okay, black need to play somewhere here. Okay, somewhere here. Say black plays this move. Okay, based on the same methods, just like in a symmetry, you can see this is symmetry. Okay, so we can also derive in the same way. Okay, say okay, white can make move another I here with the territory with the R zone here. But since we have this R zone, so why black need to block here? Since we have a R zone, black need to put somewhere here, but it can black cannot block the two pass spots at the same time. So we take the intersection here. So the only way to the only possible way to block winning or prevent white from winning is play somewhere here. The problem is you can see, okay, black cannot play here. Okay, so this end up with the proof. Okay, so we can prove that. Okay, and this one also shows, okay, if black if black has any move here, okay, in this territory, okay, black may have a chance to block. Okay, okay. So this is so-called relevance zone. So from this example, you can see, okay, the whole search tree is very small. Okay, but just based on what I say, okay, this tree is just a skewed tree. Okay, so it's not that big. Okay, so we can easily prove. But if without this method, then you got to use a lot of computing resource to solve it. So we try, of course, for 7x7. Okay, but let's see. Okay, 19x19. Okay, we pick some 106 games. Okay, from the book Life and Death Direction book. Okay, by Go Master Zhou Kun. Okay. In Chinese is called 本因坊赵志勋. Okay, and we can solve 68 of them. Okay, before our work, okay, the best one is Kishimoto and Muller's work. Okay, but of course it is quite old. Okay, 2005. Okay. And in their work can only solve 11 of them. Okay, so this is a big jump. Okay, from 11 to 68. Okay, and one of the problem is this one. Okay, and this one use a very difficult tactic called I-Chen no Shita. Okay. In Chinese, we say 倒拖穴, or that means inverted boots. Okay, a very tricky way to win the game. Okay, to make it alive. Okay, and of course, based on that, okay, of course, like most of us know, okay, transposition table can help. So you propose some lookup table like a transposition table to help to solve problems which has been solved before. Okay, so we don't have to repeat again. Okay, like a transposition table. I don't want to go to the details. Okay, but the result is, okay, we improve our solving from 68 to 83. Okay. And in international conference on Go studies in Korea, okay, last year, Zhongjin also present several interesting problems that we can solve. One of these is this problem. Okay, and in this problem, okay, the book said, okay, white A will be the only move to be alive. Okay, and from our work, okay, we find the move B is also another answer. Okay, so this shows, okay, this has some different solution from that book. Okay. And continue the following list line. Okay, Tilong also continue working on this. Okay, work on try to solve with online fine tuning. Okay, the motivation is okay because if we want to solve a very big tree, okay, then there are many when we try to search this part, okay, the winning pattern, okay, here may quite be maybe quite different from some other place. So the solution is to investigate, to keep online fine tuning, keep training the system, okay, while searching, okay. This idea is quite interesting, okay, and it's presented in last year Triple AI. Okay, sorry, should be NeoRISP. Okay, sorry. I could be should be NeoRISP last year. Okay, this is the architecture. Without online training, okay, we don't have this part. We simply manage the whole search tree here. For each leaf node, we try to prove is if we can prove this or not. Then we can select that into a jobs to worker solve it and then go back to report saying this is solved. But this one basically get learning data from the workers, okay, and then keep training that, okay, and then after for the new models, get back to the workers, so the worker can always manage the model, up-to-date model, okay, yeah. Based on this, okay, we can solve 7x7 kill goal, okay. 7x7 kill goal is a kind of goal variant. Okay, it starts with two black move, and then the question is if black can kill all the white stones, okay, can occupy all the pieces, then it wins. But if not, then white win. Okay. So this is a very interesting case for for life and death problem. As long as white becomes alive, then white wins. Okay, so that makes things very simple. Okay, and we in this paper we already solved 16 of them opening. Okay, so like this. Okay, yeah, and based on this, we expect to solve many more openings later. Okay. Now, an open question now is, will we solve the game? Okay, the whole game. Okay, that could be very challenging for us. Okay, and this is the collaboration work with scholars like Tilong Wu in Academia Sinica, and Martin Miller also involved. Okay, Ting Han Wei. Okay, yeah. Okay, hopefully you will hear some good news from us very soon. Okay. But the whole thing is currently is led by Tilong Wu, Dr. Tilong. Okay. Okay, so how about other games? Okay, we also apply that to other games like this. Okay, 2048, we use optimistic, temporal difference learning. Okay, optimistic is a key to for the game, for the model, for the program to try to dig up some new positions. So it's very good for exploration. Okay. Before this work, we already got the first ever 2048 program that can play up to 64K tile. Okay, 64K tile. I think if you have played this, you should know how hard it is. Okay. And this work, okay, we also achieve the current state of the art. Okay, this is the current result. Okay, I believe it's still state of the art. So at this moment, okay. And we also apply learning stuff for computer Chinese chess by Chen and Wenjie. Okay. And we use some kind of comparison training to make it stronger. Okay. Before that, we have no chance to win the gold. Okay, in computer Olympia. Based on this technique, we won one. Okay, we won the gold. Okay, in 2017. Okay. And this could be our earliest reinforcement learning stuff. Okay, for computer games. Okay, it's for Nexus. Okay, and it was presented in ACG 2016. Okay, and we applied that for temporal difference learning, and we reached the win rate of 15% win rate against our previous one. Okay. This one should be strong enough, but our new one can beat that. Okay. Okay. So the previous story were all about computer games, and now we try to explore the possibility of deep reinforcement learning research to other applications. First of all, we try autonomous racing. Okay. We participated AWS Deep Racer competition. It's sponsored by Amazon. It's a kind of a miniature car racing. We won several awards. Particularly, I would like to mention this one, 2022. Okay, we won the top 3 among 150,000 competitors, according to the sponsor. Okay, and this is the final.
It's a strong one.
Caption
Is it going to be good enough? Coming to the line. Let's check the time. 13.756. We have raced 160,000 developers all around the world. This competition in 2022 has covered all of the world. We've gone all around, come down to the best 50 racers, and here today, now, we've got our winner.
Okay, so we won the top 3. Okay. So our contribution is to propose some image-based regularization for action smooth. Okay, because we observe sometimes it has big shaking. Okay, so we try to minimize the shaking. Okay, to make it smooth. And at the same time, we propose control methods so it can make turn quickly. Okay. So based on this, our car can run very fast. Okay, and also has high successful rate. Okay. So this is the reason why we have the chance to win the top 3. And later on, we apply deep reinforcement learning trick to manufacturing optimization problem, particularly for job shell scheduling problems. Many of you might know, Taiwan has a strong manufacturing industry. So it's very important for Taiwan's industry. Basically, we apply this for JSP. Okay, let me probably skip this. Okay, the basic idea is the agent keep choosing a job to schedule. Okay, and so so it's quite similar to the framework of reinforcement learning. And then our result, we also use graph NN together. Okay, and our result is also state of the art. Okay, in this research. And the result is published in IEEE Access this year. Okay. And finally, about reinforcement learning from human feedback, RLHF, for large language model. Okay, this is what Sam Altman said. Okay, he said reinforcement learning works remarkably well. We and remarkably little data to make the model more useful and efficient. Okay, so you can find his talk in Lex Friedman podcast. Okay. The key here is alignments and the preferences. Okay. Basically, large language needs to align their output more close to human preference about like helpfulness, harmless, truthfulness, safety, and so on. Let's pick up the two key, helpful and harmless. So you will be able to see what happened. Okay. To be helpful, okay, when you say, okay, let me give an example. If you ask, okay, can you help me connect to my Wi-Fi? Okay, then you say blah, 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 how to do that, and then this would be very helpful. But if you say something like, sorry, I don't know how to do that, okay, then that's bad, okay, not so helpful. But what happened about if you ask, can you help me hack into my neighbor's Wi-Fi? Okay, if you want to be helpful, then you probably say, okay, sure, you can use some app that allow you to log in and hack into your neighbor's Wi-Fi. So it's helpful, but it's harmful. Okay, so the problem is, okay, so is that really good? No, actually, from harmless issue, okay, it's not so good. So it's better to say this way, okay, hack into neighbor's Wi-Fi is an invasion of their privacy, and I strongly advise you not to do that. Okay. So okay, so I just feed that into the framework. Framework. Okay, can you help me to connect to my Wi-Fi? Okay, so it's helpful. So give a positive reward. If you answer sorry, I don't know, then it's not so helpful. So it will give a negative reward. And if you say okay, if you ask us help me to hack into my neighbor's Wi-Fi, okay, you say sure you can do whatever, do some trick. Okay. Then, but this would not be good. So you got to give a negative reward to discourage agent to do that. Okay, and you better to say, okay, it's not legal. Okay, so that would be a positive score. So to encourage that. Okay, and then based on that, we can train a reward model. Okay, and then use the reward model. We can just use traditional or the common deep reinforcement learning algorithm like a PPO to solve it. Okay, so I won't go into the details. Okay, so there are a lot of variants of reinforcement learning from human feedback, like reinforcement learning from AI feedback, and direct preference optimization. Sometimes people just say DPO. Okay, or KTO stuff. For the next two, okay, it's more about preference learning, not very exact, not exactly reinforcement learning, but it's a kind of preferences just very like what we have done, like okay, say error rating stuff. Okay, okay. And then our government, we also participate the project in our government project. Okay, trustworthy AI dialogue agent. Okay, because for we are not sure the alignment problem, so we try that. Okay. Okay, so the challenges. Okay, so I would like to use the challenge to end. Okay, this talk. There are still a lot of multi-agent stuff, multi-objectives, especially for real-world stuff. Okay, there are a lot of multi-objective problems, and the reduction of of computing resource for deep reinforcement learning. And how about explainable AI? Okay. Can AlphaZero can help about explainable AI? Okay. Actually, we also have done something about adversarial attack. Okay. And how about more reinforcement learning applications on large language model? Okay, so then I would like to conclude that okay, the reinforcement learning has been very successful in many applications, including computer games, and it's really fun. Okay, with working on deep reinforcement learning, at least for me. Okay, either computer games or real world applications, and I still believe my first slides. Okay, computer games still play the role of full flight. Okay. And I would like to thank a lot of organization to donate for donation and also some contributors from our lab. Okay, so I would like to end my talk here. Thank you very much. Thank you.
Thanks a lot, I-Chen, for your very nice talk. Are there questions? So please put in the chat if you have questions. So I have one question, or I have many questions. So one is about your job shop scheduling application. So you compare to L2D, which is a standard neural network. I did not understand if you use a search algorithm with your GNN in the job shop, or are the results you show only with neural network?
You mean the job shop scheduling stuff?
Yes, job shop scheduling. So you have comparison with other algorithms. And yes, so you use only a neural network, or do you use a search algorithm with a neural network?
Let me see. Okay. Okay. Yeah, we use GNN. Yeah, reinforcement learning. In the reinforcement learning part, we use sorry.
Yes, because L2D it only uses a
DQN,
neural
of
network.
course, we tried DQN and of course also PBO stuff. Okay.
Okay. So this is just the neural network that gives you a policy, and you optimize according to this policy.
Basically, policy based would be better. Value based would not be that good. We have tried both. Okay, and it end up with policy based should be PBO. I tell you what. Okay, why policy based is better. Okay, for value based, we need to accurately evaluate the value, but the value varies a lot. Some need a lot of time and some need smaller time. Okay, so the value could be varies a lot. So policy based would be better because that just give you a direction. This one is good. This one is better than this one. Okay. But for value based, you got to predict the value very accurately, but almost impossible. Okay, for this kind of problem. So if you like to try optimization problem like this, okay, maybe a lot of NP components problem. Okay, for this kind of optimization, sometimes it's very, very hard to predict the value. So it would be better to use policy based. This is our recommendation, but of course, well, I would not say this would be definitely good. Okay, maybe there are some other good methods. Okay, on that, but according to what we have done, okay, policy based will be more important. Yeah.
Okay, thank you. So I have another question on the relevancy zone based search. So you apply this to life and death solving?
Life and death. Okay.
And so when you search a life and death problem, do you go until the two physical eyes, or do you have some knowledge, like some predefined patterns that give the solution to the problem faster than going until the end of the problem, where the eyes are done?
Okay, basically in our first paper, okay, we propose to this is our first paper, okay. Okay, about this. Okay, we propose to use, okay, suddenly don't forget. There's a there's a rule, a very neat, that can prove, okay, you can definitely alive. Okay, sorry, who can help? Okay, I forget the name. Okay, of the scholar. Okay, okay.
Is it Benson?
Right. Hey, can you say that again? Okay. Yeah, sorry.
Benson.
Benson. Right. Okay, Benson. Okay. Yeah, thank you.
So you stop when it is Benson alive?
Right.
Okay. So because there was the problem at Thomas Wolfe that used solving a completely enclosed life and death problem. And he was using the retrograde analysis of pattern to speed up the search. So that might be interesting to
Because we
kind of.
use rhythm zone. So even Benson is quite something near the end, but it can form the zone very well. So we based on that to prove. Okay.
Okay, so maybe we can thank you again, I-Chen, for your nice talk. And
Thank you.
I think there's still some time to answer a
there's some time.
question.
Okay.
In
So,
Q&A, there is a question.
are there questions in the Q&A?
Yeah.
Any questions? Okay.
So I don't see them.
Oh, then I just read out it.
Yeah.
From Bishop, do you think DRL could be the pathway to achieve AGI? If so, what key advancement or challenges need to be addressed for it to realize this potential?
Will you say that again? Okay. Which you want? Okay.
Do you think DRL could be the pathway to achieving AGI? If so, what kind?
No. Oh, no. I don't think. Okay. It might help AGI, but I don't think it will be the key stuff for AGI. We can think this way. Okay. Artificial general intelligence. The general sounds okay, like okay, it knows everything, but a lot of knowledge, okay, cannot build up from scratch, just like AlphaZero. AlphaZero is neat, okay, just because okay, the rule is quite clear, okay, but in real life, okay, a lot of things are not does not have a, a clean rule, like just like a language. Okay, there are a lot of way to say something. Okay, so there's of course we have grammar, but sometimes the grammar might out of date, it will be changed. Okay, so there's no good no rules like Go or computer games. Okay, so for AGI, it needs to also deal with a lot of real life stuff. Okay, so I don't know. But anyway, that would be also my what I can say. Okay, but anyway, I think definitely reinforcement learning is a key artificial intelligence techniques that can create new tricks or new stuff. Okay, for something like like a like a GPT-4 or something, we thought that's very strong, very good. But actually, that one learns from humans. Okay, but reinforcement learning can learn something that human does not know. Just I think Go is a typical case. Okay, if you see a lot of Go games, okay, there are a lot of strange moves or different concept from before. Okay, but this is not what our knowledge current. This is not something that human knowledge can say or something. So anyway, well, that's a big topic that I shouldn't say too much because that's beyond my knowledge. Okay, thank you. Thank you for this is an interesting question. Anyway, a very big one. Okay, any more questions?
So there is another question by Bishal, which is what advice do you have for students new to AI, especially in deep reinforcement learning?
Sorry, can you say again? Okay.
So what advice do you have for students that are new to AI
Okay.
and in deep reinforcement learning especially?
Like I say, okay, computer games plays the role of full fly. Okay, so definitely, I think the computer game would be the if you want to learn some more about computer game or artificial intelligence. Okay, computer game would be definitely the good stuff to start with. Okay, and for the computer games, of course, okay, reinforcement learning would be one of the probably the most important key. Right? Yeah. So definitely, I think it would be good to learn reinforcement learning computer games, and then you will be able to see a lot of interesting in the whole okay. Or more artificial intelligence. You may have different view about artificial intelligence. So I think anyway, at least for me, it's a very interesting. Okay, it's a very fun to work in this direction, and actually I think I learned a lot from that. Okay, yeah, thank you for the question.
So thank you, I-Chen.
Thank you.
Maybe we can close the session now.
Okay.
So thanks a lot for your very interesting talk. Eager to meet you again sometime.
Yeah. Welcome to Taiwan sometime. Okay.
Okay, thank you very much, I-Chen, for this wonderful talk. Thanks, Tristan, for sharing this keynote.